Toplanan ve geri dönüştürülen plastik ambalajlar yepyeni ürünlere dönüşerek hem ekonomiye katkı sağlıyor hem çevreyi koruyor. PAGEV, plastik sektörünün birleştirici gücü. Toplanan ve geri dönüştürülen plastik ambalajlar yepyeni ürünlere dönüşerek hem ekonomiye katkı sağlıyor hem çevreyi koruyor. PAGEV, plastik sektörünün birleştirici gücü.
Thank you, Mr. John. Okay, I'm done. All right, let's start again. I'm going to talk about normal stresses. This is a rather difficult concept, and in fact, I have a quotation from a book by Robert Byron Bird. He's from the University of Wisconsin, and he is one of the changers of chemical engineering curriculum. Armstrong is from MIT, and Hassager is from the Technical University of Denmark. And the word that they say, read this here, a fluid that's macromolecular is really quite weird. Weird, in English, it means strange, but it's a rather unusual word. You never see it written in scientific books. I never see this word weird in any other scientific book, but it is here, which means something very, weird, unusually strange. Big normal stresses the fluid possesses give rise to effects quite spectacular. And one of them is the Weissenberg effect. That is, if you have a shaft rotating in a beaker, the polymer tends to rise up in a beaker, very strange. And there's some other more strange effects. You will see in the book, you'll see more strange effects that I have them all there. I will not have the time to show it here, but in your book, you'll see them more. Extrudate swell. You see, if I have a Newtonian fluid, the diameter of the extrudate is about the same as the diameter of the die. It's a little bit larger, but not much, 12%. For a polymeric liquid, I have measured up to about 400%. One company, people from one company told me that they can go up to 700%, very, very large. But I've never seen it that much. But 400, yes, I have seen. So, again, this is due to the so-called normal stresses. Now, I try to give an explanation of this phenomena, of this Weissenberg effect, and I really have to demonstrate it. Perhaps I can use this as the axis that rotates. So when you have long chain polymers, they act like springs, and as one author put it, you rotate it, they extend, and they try to strangulate, the polymer, so they push it that way. Well, this is interpreted as normal to the direction of the flow. So you have a shear flow, and you have a normal force. This is what happens. You will see even this is a little bit mathematical, this graph. What I'm saying is that right here, read this in the book because it's complicated. I have shear flow, and while I'm shearing, I'm also extending the polymers, right? Like shearing in a polymer solution or polymer melt implies also extension. So the sheared polymer is extended, and because of that, it does have a number of different properties. How to measure it? If I have the corner plate, we rotate, the polymer wants to go up, but there is the cone, nowhere to go. It gives a force, and the force is the normal stress. We can get it from there. What is the importance of normal stress in polymer processing? Well, it relates very much to broad molecular weight distribution. If I have a polymer with long molecular weight chains, this polymer has high normal stresses. And they mean a lot. Like high normal stresses, they have very large implications. And I say here, you see, the normal stresses are very large. And products with very large stresses, right? I produce something by extrusion, or let us say injection molding, right? And then when it comes out, I lower the temperature and I freeze it. But I freeze the normal stresses inside the part. So if I heat it again, the normal stresses, all the stresses, but the normal stresses are usually about 10 times larger than the shear stresses. So if I heat it again, the normal stresses are released and the material becomes warped. I have a dramatic case, I could not find it. We had a calculator. A year ago, I had given a course in Greece. And my colleague went to Crete, the island of Crete, in the summer. It was very, very hot. And of course, inside the car, he left the calculator, a hand calculator, in the car. And when we saw the calculator, it was completely distorted. But the funny thing is that the electronics were working. But the calculator, you know, it was a square, and this thing had been completely warped. My next lecture, probably I'll try to find it and put in the picture. It was a commercial item, nothing that I did it in laboratory. It happened by leaving a calculator in a car under very high temperatures in the trunk of a car, you know. So the question is, I mean, all right, it's an interesting phenomenon, right? Did I ever solve a problem by measuring normal stresses? This is the question. I mean, this course is aimed at problem solving. Yes, I did one problem. In fact, Evan Mitsoulis was my graduate student at the time, who is here, first row. And the problem that we had is what I showed to you before. We had done some work in calendaring, and we showed some instabilities when you have two rolls and so forth. And the company was producing the windows for these Amtrak trains. And they told me early on that some people at night, during the day was okay. At night, people getting dizzy, like drunk, they tell me. You know, how come? That was the process. So we had again the same problem. Resin A, no problem. It was the competitor, of course. Competitor pushing through the calendar, no problem at all. My customer, I said, well, the chemist, I talked with the chemists in this company, United States company. And they said, between resin A and resin B, there are absolutely no differences. So they said, probably the problem is in the machine, all right? Extruder, calendar. But the question was, how come resin A had no problem, and same machine, the different resin has a problem? Well, it's got to be the material, right? Or something with the conditions. You know, this is, you know. I said, well, I said, we've got a problem. Evan Mitsulis did a computer simulation. This is a repeat because the original, we did not have colors, but we repeated Evan's calculation. Well, nice flow. These people thought in our publication with Evan Mitsulis, we had some instabilities here because of the geometry and the conditions. But in my customer setup, nothing of like that. There were no vortices, nothing. Just nice flow, you know. So the problem was there. I tried to explain, and I found that there was some waviness on the surface, very, very little. And I related it to the frequency of oscillation of the rotating cylinder. It wasn't perfect, you know, they measured it. I said, could you measure it? Yes, they did. Measured it, I said, oh, we have the same frequency. Well, again, the same frequency, but again, how come? Resin A, no problem. So I said, well, the two resins are probably the same, are not the same. But the chemist, I remember the chemist, they said, listen, this patent of PMMA production had expired years ago. Same, they had the catalyst, they had the conditions, everything. I said, we did everything like the competitor. We see no difference. I said, well, there's got to be a difference. So we started different. You know, I said, the only way to determine very, very small differences in the high molecular weight tail, the very high molecular weight tail, is only if you do normal stress measurement. And yes, they did. The one resin and the second resin, the first resin, the good one, had very high molecular weight tail. It was giving, because it was giving more swell, essentially. But the wavelength of the fluctuation was large, and the people were not bothered, you see. Whereas the other one that had less molecular weight was giving like this. It was responding. The more elastic one was better. And the differences were detected by just measuring the molecular weight distribution. They did the measurements. I did not have the equipment at that time. They gave it to a third party, and they said, yes, the two resins are different. So we identified the problem and the differences. They fixed it. Problem was solved. You see? So there's things that you don't expect, because for them it was a very puzzling question. You see, how come one resin, and they thought that the resins were identical, but they were not. They were very minute quantities, right, of very high molecular, probably was less than 1%, in the, just a small amount. But this small amount had a very big effect on essentially swell. Swell is related to normal stresses, and it gave very big problems. Okay, now the next thing is stress relaxation in dynamic measurements. One thing that we know very well is that if we apply shear to a polymer, and let us say we have a rotational rheometer, we go up to there, and all of a sudden we stop. Then the stresses will relax, but it will take some time, right? Now, if we have a Newtonian fluid, the relaxation will be instantaneous relaxation, right? So there's difference between Newtonian and non-Newtonian fluids, polymeric fluids, in this context. And now I have some measurements that were carried in my laboratory, and we have different resins, and you will see this resin right here, the stresses relax very fast at about 10 seconds. They are practically zero, but if you take that resin, it takes a long time for the stresses to relax. So this shows that polymers can be characterized by how long it takes for the stresses to relax to zero. So it's a way of differentiating stresses. And this has a lot of implications in frozen-in stresses, like if for the stresses take a long time to relax, right? I will freeze, I will cool the, let us say, the injection molded products, the pipe. I had one pipe. It was just a nice pipe, and all of a sudden it started, getting like flour, it was a question of cooling, and that gives that. And it, you can easily see what happens if I have a hot inside product, cold outside, and of course the hot inside will strain more. It will happen with anything. However, it will happen more, with broad distribution, where I have high normal stresses, so that you relate warpage to normal stresses to, so it's another way of looking at this thing. Now, the measurement of stress relaxation, as I presented, like I have an experiment, I apply shear, I stop, and I measure. As it was done, it's a good test, but it is a difficult test. You hardly see any measurements of that nature, except in universities, but it's just not a standard way of characterizing the relaxation behavior of polymers. Because this measurement depends very much on the instrument. Like the instrument itself, the metal, has some relaxation of its own, and what can you measure, like the sensors that you have? So it is not a standard method. The standard method is to use what I call dynamic measurements. You use the sinusoidal deformation, and you record the results. And then by recording the results, you can find out certain important information, like you apply sinusoidal strain, you get a sinusoidal stress, all right? There is a way, and I have in the book, I will go here very fast due to the shortage of time, but in the book I have much more information explain this. One interesting thing is that if you do sinusoidal, you get a viscosity from this sinusoidal deformation that is a viscosity similar to the steady state one. So this is the famous Koch-Merckx rule. That is not always valid, but it's valid for many commercial polymers. So a way to measure it. In fact, to do that, we do what we call small amplitude oscillatory shear. It's a standard method. You will find much more information in the book of how those things are done. Lately, if there's anybody from a university, you will see that the popular thing today is to do large amplitude oscillatory shear. I'm not sure, well, at the moment, it's not terribly useful for practical problems, but the small amplitude oscillatory shear, you get a lot of information about the polymer. So I have a whole chapter in there, maybe it should be about 20, 30 pages that explain in a rather simple way what you can get out of this in the book. Now, I will not say anything about it, but it is there for you to see. Now, the second thing is about the role of shear in elongation, in mixing. Because polymers are mixed, they are compounded with pigments, reinforcing agents, fillers, other polymers. And this is sort of over the years, doing work with companies as a consultant. I realized that everywhere I go, I see polymers that are mixed everywhere. I mean, I was producing, one of my customers was producing a very high quality film. And, you know, I thought it was 100% virgin polymer. However, I did realize that they were loading it with 40% calcium carbonate to reduce the cost, obviously. And wherever I go, there's always, here in Turkey, one of customers of my customer, they were producing pipe, and I know they were putting in calcium carbonate, and of course, you have to know what are the problems associated with mixing to polymers. You know, somebody was telling me they are blending, somebody was telling me about mixing two polymers. Like, polymers don't really want to get mixed, you know, put it that way. They don't like each other. And you really have to know what you're doing. So I'll show you some examples, because so what we have to do is that you're going to have a minor component must be dispersed, and the word dispersed means it must be broken up. It must be reduced in size. And then it must be distributed throughout the polymer matrix, right? So it is easier said than done. And here I have an example of all the possibilities. As you can see here, I have bad distribution and bad dispersion. I have bad distribution because I have something here, something there, very little there, nothing there. Bad distribution. Dispersion because I did not break anything. Here I have good distribution, but dispersion is bad because I did not break up the agglomerates. I have to break them up and then distribute them, right? Here, I did manage to break them up, but the distribution is very bad, you know. I have one group right here. So I really have to do something like that, to break it up in very, very small dimensions and then distribute them throughout. And this is a real problem. It looks like theory right here. Let me just tell you one problem that I had. It was a customer, and he wanted to toughen polypropylene. How do you toughen polypropylene? You put rubber, as you know. Ravago people would know certainly about that, right? You know, the rubber that you put in, that he wanted at least, I don't want to mention anything about a company, I don't know what exactly they're doing, but my customers, rubber had a viscosity about 10 times larger than the viscosity of the polypropylene. And the results were not very good, and you'll see why. You see, like, and they had the right extruders, and they were doing a lot of material, about 10 tons an hour. Twin screw extruders, very good machines, but it didn't work. And, you know, you wonder why. So he really wanted to have something like that. And he knew about the dimensions of the particles that they should have had, but they did not. The particles were large, well distributed, but the particles were large. Was probably a picture, a version probably like this he had, like they were too large, the particles, and he wasn't happy with the properties. So he came to us to try to solve the problem. So how do I break up? Dispersion is determined, of course, by the balance of the cohesive forces that hold the solid agglomerates together, and during the process of mixing in a mixer, in an extruder, or whatever, you develop hydrodynamic disruptive forces, and of course, this is what is going to lead to good dispersion. Well, dispersive mixing is dominated by the stresses that I'm going to develop. And we need a critical stress to break up. Like, you try to break anything up, you have to pass a critical shear stress. You can apply it, but it may start moving, turning around, whatever, it doesn't break. But if you pass a certain level of stress, then it breaks up. So for this thing, I will tell you what happens with when you have one liquid inside another. Like, let us say you have water and you put an oil drop, right? Well, you start shaking it and not break it. You see, like, you don't break the bottle. So what it is, like, it is the interfacial tension of the oil drop inside that keeps the drop together. So somehow the forces that you apply when you shake or when you pass through equipment must exceed those forces, and we have here two numbers, the capillary number and the viscosity ratio between the matrix and the polymer to be dispersed. And this becomes obvious in two curves that were developed by Grace. These are referred to as the Grace curves. The publication was in 82 or whatever. And let me explain briefly what that means. Right here is this capillary number. It tells you something about the surface tension or the interfacial tension between the drop and the matrix around it, right? So, and this is the ratio of the viscosities. And Grace, in terms of theory and some experiments, found out that if you just have only shear flow one, it turns out that if the viscosity ratio, if the polymer to be dispersed has a viscosity 4 times larger than the matrix, the limit is 4, which means if I have inside the bottle, right, a drop of a oil, let us say, or whatever, which has a viscosity 4 times larger than the viscosity of water, no matter how much I'm going to shake this, it will never break up. And this happens in an extruder. So that if I have shear flow, right? So if the flow is just shear, no matter what I do, no matter how much I jump around, no matter how I shake it, the droplet will remain unbroken. All right? Nothing will happen. If the ratio of the viscosity is larger than 4. This was theoretical for Newtonian fluids, but it does hold approximately for polymers. And this is important because in a single screw extruder, really a single screw extruder is mostly shear flow. You need elongation of flow to do that. In fact, the second figure over there, you see the same coordinates. Here is the surface tension, here's the ratio. If I have elongation of flow, we have no limitations in the ratio. I have no limitations in the ratio of viscosities to break up. Can do anything. Like I can put 100 times larger viscosity into the matrix, all right? And this will break up. But I must have elongation of flow. And elongation of flow is not easily generated. So to have elongation flow, we must be somehow stretching. Where can you do that? And I say, single screw extruders, you may add, and I'm sure most extruder manufacturers, and I have dealt with some extruder manufacturers from Turkey, yes, they add dispersive mixing sections, like the Maddock mixing section. They are dispersive, they are called dispersive. They have some regions of elongation of flow. But, you know, they are not good, you know, as good as I like them to be. My customer from Japan was from a Japanese company. They wanted to mix toughened polypropylene. The rubber had roughly 10 times higher viscosity than the polypropylene. Could they do that in a single screw extruder? I would say no, no matter what I do there with. So I really need a twin screw extruder, and in twin screw extruder, I can easily generate regions of elongation. Now this is, as you can see, this is a co-rotating twin screw extruder. And as I go there, we have a lot of squeezing that's going through, right? The red area is squeezing. And squeezing means that I'm forcing the polymer through a narrow gap. I'm stretching it. This is what is required. And not only that, I really need a good design of an extruder. In this picture was given to me from Charlie Martin. Yusuf, you probably saw he gave a talk. It was from his talk in Boston, actually. This is very nice. This tells the story, because he said that if you have a narrow mixing element, knitting element like this, you see the polymer is escaping from the sides. You see, the polymer is escaping from the sides. And this is really characterized as a dispersive fluid element. Whereas if you have a wide disk like this, you see, you force the polymer over there, and you do get elongation of flow, and this is really the dispersive element. You see, if it's like that, so I suspect when my customer came and told me, we're trying to mix 10 tons an hour, and we have twin screw extruders. The extruders are co-rotating. Everybody knows that co-rotating extruders are good mixing machines. Probably, because I do not know the equipment, and they didn't want to show it to me. Probably they have narrow elements. And then I told them, well, you better use wide. And that was the answer. So you have to use wide elements to really have elongation flow. And if you have elongation flow, you get the job done. And he did the job done. Got the job done with wide. And this, it's a nice picture. And I asked Charlie Martin from Leistridge. I saw him in Boston last November, and he gave it to me, and I thank him for that. Distributive mixing, also known as laminar mixing, is quantified by the growth of the interfacial area. There have been a lot of analysis, and it is like the process of making dough, like my grandmother used to do. I remember used to spread the dough, cut it and so forth. This is perfect way of mixing it. Unfortunately, it's difficult to do it with polymers, right? But just essentially, you have elongation of flow also, right? You stretch it, you spread it, stretch it, fold it. I mean, in retrospect, it was the perfect way of really distributing, and this is the way the food we eat, bread and so forth, that's the way it's done. The question is to do it in a machine. And a good way to do it in a machine is static mixers. You see, static mixer, what it does, you you have flow like this, you break it up, you turn it around, and you break it again, you break it around. So I recommend to a lot of people that when mixing is not so good, especially dispersive mixing is not very good, I say, well, use a static mixer. It's not very expensive. It does not cause very much pressure drop. And this is also good for temperature homogenization. Very good for temperature, you know, and I've seen it. We're talking about pipe, for example. One customer had a problem, but we had long melt tubes, and I was wondering what is happening in there with temperature distribution. And I said, well, why don't you add a static mixer at the end? They added the static mixer, never heard from them again, which means they didn't want to pay me more, and that was it. So problem was solved. Because it's essentially, the static mixer is exactly doing what my grandmother used to do with making dough, you know, the so-called baker's transformation. So static mixers are very, very important for homogenization, distributive. So you must distinguish between the two. Like you would need a co-rotating twin screw extruder to do dispersive mixing. And then you might have already good distribution as well in the extruder, but if it doesn't, or if you have a single screw extruder, good idea to add the static mixer, you know, and I solved with a couple of customers problems of that nature, better distribution and also temperature homogeneity. Now, beware. Many problems may be misdiagnosed as due to dye or raw material, but frequently they relate to poor mixing. Check the extruder and screw if suitable for good mixing, dispersive and distributive. I mean, this is the case all the time, and I'll give you a problem. It's a European problem, and it's a company making fibers, actually fibers, and from the fibers they were making ropes for ships, actually, for large diameter ropes for ships, and they did have problems, and they told me about it. And first thing they reported to me was, before I saw the extruder, they said, gee, the fibers come out, and there's a lot of powder, and the quality is very poor. And then they suggested, because they know that I have developed and I sell computer simulation software, they said, would you be able to design a new die for us? Well, the die was very, very simple. You know, essentially, it was a die. It had 500, looks like that, you know, in the shape. The top, it was something like that. It had 500 holes. The holes were around 1 millimeter in diameter, 10 millimeters roughly, converging. I checked, you know, did a simulation. There was nothing to design. I mean, they were good. I mean, you know, what can you do to a hole, essentially? And when I checked the design of the holes, I could not really see any possibilities. And then I requested from them, I said, well, can you send me a picture of the screw or a blueprint of the screw design? And they sent it to me, and I realized that there were distributive mixing elements, and you will see in the afternoon about those, but nothing, absolutely nothing to break up, nothing, no dispersive elements. I said, would you please buy a new screw? And I recommended a manufacturer who was also a customer in the United States. Well, they ended up buying one new screw. It worked very well because it had some kind of a Maddox mixing element. You'll see this element in the afternoon, right? So they changed the screw, and then they ended up buying 4 more screws. They replaced the screws in other extruders. Simply because the new screw had dispersive mixing section that was a Maddox type. Not exactly, but one type of Maddox that had elongation of flow, and this was causing the dispersion because although it was polypropylene and HDP, well, I told you, they don't like each other. They don't want to be mixed, right? So what they were extruding before I arrived there, there were 2 polymers blended. One side was polypropylene, another side was the HDP, and whatever was coming through the die, and then they had a problem because essentially they were not mixing. So mixing is a very, very important problem, and make sure that this is not the case, because a lot of people may say, well, it's the die, it's the extruder. Well, it's the screw, essentially, the screw design. And we'll talk about mixing screw designs in the afternoon. Now, another important rheological problem is the phenomenon of extrudate swell. As the polymer exits from a die, it swells. And as I told you, swelling is a lot. Now I'll show you another picture of how things really happen. So you can think of an imaginary cylinder inside. It gets stretched, extended through when it passes through the die, and when it comes out again, it swells. And the value of the swell, it decreases with the length, and eventually you reach some kind of an asymptotic value. But you see, if the die is very short, that is, we have a die of 0 length, we have the largest amount of swell. Why? Swell is primarily, as I said early on, is due to the release of the normal stresses at the exit, right? However, if I have a short die like this, 0 length, right? We also have a memory of entrance, like the polymer extruded remembers that inside the reservoir was short and fat, right? When it gets through the die, it gets stretched and it thins, eventually tries to recover. But if there is just a very short die, it doesn't have time to forget, and it gets, so this is an important problem to remember, that swell
depends also on the length to the diameter ratio. The shortest die will give you the largest amount of swell. Okay? Now, if you have a long die, the thing to look at is the distribution of the molecular weights. If I have a polymer with broad molecular weight distribution, that means I have a lot of normal stresses. And the normal stresses will give you the largest amount of swell. All right? If I have a narrow molecular weight distribution, I will get the smallest amount of swell, right? So the distribution of molecular weights will determine whether I have large swell or small swell. Do I have a problem on this? Yes, I did. Well, that was actually in Venezuela. I remember it was years ago. I went there before these recent problems they have in Venezuela. And I talked about swell and broad molecular weight distribution and whatever. And I got a call from one of the participants of my short course. He said, I have a customer, and the customer is complaining because when they produce the Venezuelan resin through the equipment, an extruder making sheet, it was 15% thicker. 15% thicker. However, they were not selling by weight, they were selling by the square meter. And it says, well, you know, we're losing money because our product is 15%. I suggested, well, maybe you can reduce the production rate, shear rate, but they didn't want to do it. You know, they said, well, what can I do? I said, well, I showed the previous graph. I sent him again. I think I had this graph in the lecture notes, and I sent it again to him, and I said, listen, your product probably has broader molecular weight distribution than the competitor's product that is used by your customer, all right? And in that case, that was the problem. He talked with the chemists, the polymer production engineers, and they somehow, through catalyst technology, whatever, temperatures, they produced a more narrow molecular weight distribution, and more narrow molecular weight distribution has less normal stresses, and yes, the product was less thick. I do not know if they managed to get down to 15% or not, but they were happy after that. It was just that, I mean, a question of extrudate swell. Okay. Now we have another problem. Well, there are three important defects. One of them is called the Sharkskin. The second one is melt fracture. The third one is die lip buildup, which is called drool. The word drool, in American English at least, I'm not sure in British English, But drool means, say, something coming from the lips, like a dog, for example, running, and it's coming out from his mouth. It's called drool. And that's in fact, lip buildup is in books only. In industry, everybody talks about drool, you know. So these are the three problems. And this is a picture of sharkskin. Take a look at it. And to recognize sharkskin, you must have ridges perpendicular to the direction of the flow, as you see here. You see, like the original, of course, was about 2 millimeters in diameter. Now it's enlarged because enlargement on the slide and eventually enlargement on the projection. But you see, we extrude this way and we have perpendicular ridges. So this is what characterizes sharkskin. If you do not get perpendicular ridges, well, it is not sharkskin, it's something else. I'm saying that because very frequently I'll get a phone call from a customer and he will tell me, oh yes, we've got sharkskin, could you do something, and so forth. If I get a sample, I'm looking at that, right? So take a look at it. It must be perpendicular to the direction of the flow. If it's not, if it is in the direction of the flow, well, it's something else, all right? So, and it is visible to the naked eye. This is very important for anybody doing blown film, flat film, anything for the packaging industry. Who is here from packaging industry? Okay? In the packaging, if you're in the packaging industry, this can be a very serious problem. Now, sharkskin happens, as I mentioned over there, the shear stress in textbooks is 0.14 megapascals. And the corresponding rate of shearing. And however, if I increase the flow rate, I'm going to get to more distorted extrudates. The first one is known as spurt. We may have a helical distortion. We may have gross distortion. And this, beyond sharkskin, they're usually referred to as melt fracture. There is a solution. Minute quantities of fluorocarbon polymers minute amounts of fluorocarbon polymers, which are very high priced, are used as processing aids. And these are fluorocarbon polymers, and I have to tell you a story. Stories always are good. To see how those things, the fluorocarbon polymers, were discovered in a way. It was with the introduction of LLDP, linear low density polyethylene. And linear low density polyethylene is not very shear thinning. And you reach the value of 0.14 at rather low rates of low flow rates. And they wanted to increase. And somebody in DuPont, Canada, is somebody from DuPont here? DuPont, Turkey? Somebody I saw in the program. On the other side, okay. somebody from DuPont, Canada, was adding Teflon in the LLDP. Well, they did not consider it as an important discovery or anything else. They said, well, the customer has a problem. Give him some, how to solve this problem. We want to make the sale, to make some money. You know, put it in, 1% or whatever. And Sharkskin is postponed to higher flow rates. Okay? They did not claim any patent. They did not claim any innovation. They did not even tell the parent company, DuPont in the United States. Well, it happened that there was a holiday in Canada, and a customer from Canada wanted to buy Teflon and could not get hold of the offices in Canada, and phoned the parent company. And they said, I'd like a ton of Teflon. And said, well, what do you do with it? They said, well, we add it in LLDP. What sort of crazy idea is that? Like, I mean, Teflon is about 30 times more expensive than LLDP. 30 times. I mean, what's, you know, would anybody do that? They said, why do you do it? And eventually, they figured out what is happening. And what is happening is that the Teflon, because it's slippery, as you know, it promotes slip on the surface and postpones the phenomenon of Sharkskin. Now, the other phenomenon that I mentioned is dilip buildup, or, well, dilip buildup only it appears in books, actually. It is not related to Sharkskin or melt fracture, but it is a gradual deposit of material on the dilips, as I have sketched it over there. And I think, do I have a picture there? No, I don't. I have a picture in the book, a real picture. Well, how does this happen? I remember I was at General Electric way before it became SABIC, down in Schenectady, New York. And I gave a talk on instabilities in polymer processing, essentially talking about melt fracture, Sharkskin, and when they occur. And I did talk a little bit about dilip buildup, as much I knew then, and people were listening. And at the end was a young woman said, okay, I'll show you our research. And what they had done, they had took a video of an extruded strand of a polymer. They have the video over there, you know, for hours, like I think it was 8 hours video. And then they speeded up the video. And we could see that polymer, you know, was just smooth, you know, nothing was happening. And all of a sudden there would be a little drop coming out, stuck. And then after a while, you know, it was speeded up, like the whole video was about 8 hours, and then it would see the speeded up version. Every so often there would be a little drop corresponding to perhaps a few minutes, and then another drop and another drop. So it was not a continuous effect, but rather it was a discontinuous effect happening from time to time. And you know, the visit there, I gave a talk about those phenomena, but I knew very little. But by visiting, I learned a lot. And then they told me that the deposit was very rich in low molecular weight substances, and there were some fractions of the polymer with low molecular weight. There were some pigments, and that was the case. Then I had another problem that came from Japan, and they had solved the problems themselves. And they said, we have the following problem. Why we managed to solve it? How was the solution? They had a sharp dye. It was polycarbonate for, I think, fiber optics, which had to be very long, all right? Now, if you have this situation over here, and you extrude for a few hours, you have to stop it, clean the dye, and start again, and they want a very long fiber optic wire. And they said, if we have a sharp corner, we can run the extruder without cleaning for about 8 hours. When they put it there, round it a little bit, what we call flare. You open up the dye, a little bit. Wow, we can go for days, 6 days, they said. Why? Well, I did a computer simulation, and I found out by opening up just a little bit. I think it was an angle between 6 and 12 degrees. 6 and 12 degrees helped quite a lot because you reduce the level of shear stress. So the reduction of shear stress was the main factor in that the problem was solved. I had another problem, again on dye buildup. It actually came from Turkey. And it was a company which I presume it was an Indian company near Istanbul. And they said, I don't remember the people, but I think it was an Indian company. And they said, we do not have any problems in the summer, but we have problems in the winter. And myself, having been born not too far away in Greece, I know that in Greece, we do have we have rather humid winters and rather dry summers, at least in my time when I was born. And in the United States and Canada, it's the other way around. Like we have dry winters in Canada, it's very, very dry. But the summer is very wet, and they were kind of confused. It doesn't happen in the summer, but it does happen in the winter. So it's moisture, especially if you're doing polypropylene. Moisture, although polypropylene is not really absorbing water, but it can be enclosed and mechanically, and that small amount of water actually contributes to dye lip buildup as well. So many additives cause the severest buildup. So removing humidity from the resin improves the situation. Resins with wide molecular weight distribution, MWD stands for molecular weight distribution, cause more problems. If you have missing plating on the dye surface, if you design a dye and if you have any what we call scratches, any nicks on the surface, they are going to cause you a lot of trouble. Any kind of surface imperfection will cause you a lot of trouble. Fluorocarbon polymers like Teflon, again, they are very beneficial because they promote a lot of slippage on the surface. Now, This stuff, I don't think I have any. Okay, this is it. I'm not sure I can go back. But can you go back to the previous? No, the last slide.
Last slide?
Last slide, yeah, last slide. You can go back.
Where is it?
Just keep going, the last slide. Yeah, last slide.
This one?
Yeah, the last slide, okay. Okay, just leave that one. In an email that was sent to you last night or this morning, we have included, there's a book. This book is presently about 250 pages or so. I expect that we will complete this book by the end of this year. This is a preliminary edition. The first edition will be out by the end of this year. But this book includes several chapters about basics of polymers, the stuff that I talked about, viscosity, about analysis of the capillary rheometer, analysis of a melt indexer. For the melt indexer, I analyze, and it says, yes, you can use it as a low-tech capillary rheometer, but be aware that there's some errors, and you can assess those errors, and it is up to you to decide if you can use such an instrument, because a melt indexer will be, let us say, you can buy a good one for $10,000. If you want to buy a good capillary rheometer, you probably need about $100,000, and if you want to buy the top of the line rheometer Guthford, probably $300,000. So pick your choice. I mean, but I analyze. You will see. I have, for example, I take the melt indexer and analyze it and say, where do I have errors in the melt indexer? Well, where do the errors come from? First of all, we have the entrance. The die in the melt indexer has L over D, length to the diameter, only about 4. Okay. Which means that at the entrance, from the reservoir to the capillary die, at that point, I do have a lot of pressure drop. I estimate it. It is going to be very large for polymers that they have high melt strength, like branch polymers. Not so large for linear. So if you're trying to evaluate an LDP branched, the errors would be large. If you are doing the same thing with a linear low-density polyethylene or polypropylene, you're probably okay, but you can assess it so that I have the derivation of all the equations in there. In terms of the rheological measurements, things that we do not talk very much about is the small amplitude oscillatory shear. I said this sinusoidal application of sinusoidal strain is the best way to learn about the relaxation behavior, the viscoelastic behavior of polymers. There I have some very simple examples. I give you the information. I calculate relaxation time. What is a relaxation time that makes physical sense, right? So with that, I think you can get started, and you will be able to learn whether you need more from this kind of analysis. Because you may say, I will use you, Abdullah, in machinery business. Abdullah, let us say, he's going to say, Microsan is manufacturer of machines. Why would I care about polymer behavior, and you ask me to study small amplitude oscillatory shear? Well, for designing the machine, probably you do not need it. Maybe you can get some information. You can get easily shear viscosity. But Abdullah will say, gee, I also have a capillary viscometer. Yeah, well, you can do one, you can do another. But where you may have a problem to solve is it will come not from you, from your design of your machine, but it will come from a customer. And the customer will say, give you a problem like the one I had before, several times. I have your equipment, I bought it from you, I paid a lot of money, right? And I have this resin, and it's producing pipe. And this pipe has the following problem. And of course, he's going to blame you. He's going to blame the machine manufacturer first. But is it really the machine manufacturer? Or is it the polymer? Because I gave you examples that was the polymer, you know. I'm making this pipe, and I make the pipe, he will say, oh, I should tell you that one. I make the pipe, and I put it on the ground, and it has a lot of environmental stress cracking. Okay? And you might say, well, you know, and it's your extruder, and so forth. Well, since we're talking about it and about pipe and so forth, I'll tell you another problem that I solved. All right? How I solved it. They were making in Alberta, Canada. Alberta, Canada is a huge area, not very large population, a lot of farms. So they were producing a 2-inch, 5-centimeter pipe for gas distribution. Gas distribution. And they would put it in a big roll behind a tractor. They have it behind a tractor, they go into the fields, and then bury the pipe. Okay? 12,000 miles of it, miles, multiplied by 1.6. Those days we had miles. 1.6, you get the kilometers. All right? Almost 20,000 kilometers of pipe for gas distribution. Now, this pipe was delivering gas to agricultural cooperatives. However, there was a defect, a hole, 2 holes per 100, I think it was a hole about 100 meters, something like that. It was a lot. A lot of gas was going out. About half the gas was going out, and half the gas was delivered. The farmers did not want to pay. And then they said, well, why do we have this problem? Investigation, they went to the lawyers. The extruder went bankrupt. Trouble between the extruder manufacturer, and the resin producer. Now, the resin producer, this is the point. The resin producer had supplied a slightly different resin, which was only larger, higher density. Higher density of HDP means I have higher crystallinity, and the material is more prone to environmental stress cracking resistance, because these people were extruding and they were saying, well, through our machines we're extruding HDP before. The difference was that the new polymer was higher density, more prone to environmental stress cracking resistance, and that was the problem. And the extruder went bankrupt, the farmers did not pay, and then the banks, I do not know what happened, but the banks and the resin producer had some kind of a settlement. Okay, we have reached almost, well, it's 12:26 or so. We will break, and in the afternoon, we'll talk about extrusion. We are going to start at 1, what time is the? 1:30. Okay. We start right here at 1:30 sharp. Okay, thank you very much. Non può essere, non può essere.